Hey ChemStars, welcome back to some more Chapter 9 Stoichiometry homework. Today we're going to be focusing on mass, volume, and particles. If you're in level 2 Chem, this is going to be your pages 5 and 6. If you're in level 1 Chem, this will be approximately the same as your pages 6 and 7. There'll be a little bit more help here on some of the equation writings. Okay, let's get started. So let's look at problem 1. Remember, this should already have been attempted on your own, and now we're just checking our answers. So number 1, determine the mass of lithium hydroxide. That means they want the grams of lithium hydroxide produced when 0.38 moles of lithium nitride reacts with excess or with enough water, according to the following equation. So you should have balanced it yourself. If you were struggling balancing it, one little trick is you can write water as HOH. Then you can balance your hydrogens by themselves and your OH, your hydroxides, by themselves. Remember, only moles go into the BCA table. I want you to rewrite this on your homework packet, circle it, star it, whatever. Only moles can go into the BCA table. And the other thing is, the BCA table only gives out moles. So anything that goes in is going to be a mole, anything that comes out is a mole. Now this problem, they want to know mass, and they gave us moles, so we have one hurdle we have to address there. Okay, so let's see, what do we have? We have 0.38 moles of lithium nitride. We can just plop that straight into the BCA table, no conversions needed. So 0.38 moles of lithium nitride, going to use it all up. There's going to be excess water. How much water am I going to use? The coefficient, what's given in the problem, is going to be 0.38. Then I've got to figure out my mole ratios. Remember, the mole ratios, they all come from the balanced chemical equation. So the ratio of water, the unknown, to the known lithium nitride is going to be 2/1. The ratio of the ammonia is going to be 2/1. And the ratio of the lithium hydroxide is going to be 3/1. Okay, so let's say we have a lot of water and we use up this much. How much is going to be left? A lot of water. Before the reaction starts, do we have any ammonia? Nope. But during the reaction, we're going to be creating 0.38 times 2/1. So do some fast mental math, or maybe use a calculator. And what's that going to come out to be? So we're going to have 0.38 times 2/1, 0.76. So it's going to be, we've created 0.76 moles of ammonia. Now, how much lithium hydroxide have we created? 0.38 times 3/1. So 0.38 times 3/1, 1.14 moles. 1.14. Remember, this is moles. We only can get moles out of the BCA table. Did they want moles? No, they wanted the mass in grams. So we have to do a little bit more work on that one. Okay, level 1, you might have grams written here, so you'll have to do an extra step. You'll have to convert, and I'll post a separate answer key for you on this first one. Okay, so 1.14 moles of lithium hydroxide. Now we need to get from moles to grams. Well, that should ring a bell in your head. Molar mass, periodic table. We've got to go to the periodic table, so get out your periodic table if you haven't, and we need to find lithium hydroxide. 1 lithium, 1 oxygen, 1 hydrogen, 23.95 grams per mole. So we can plug that into our problem, 23.95 grams. So if we look at that, my moles will cancel. I'll be left with grams, and my final answer is going to be 1.14 times 23.95. 1.14 times 23.95, and that will give us 27.303 grams. 27.303 grams. Now you're probably thinking, what about sig figs? Look back up here. 2 sig figs. 2 sig figs. So that will round to 27 grams of lithium hydroxide. Good. Let's move on to the next problem. Okay, so for our next problem, carbon monoxide reacts with oxygen to produce carbon dioxide. How many liters of CO must be used in excess? I don't know why it keeps jumping. How many liters of CO must be used in excess oxygen to produce 14.7 moles of carbon dioxide? That's A. And there's a second question for B, but let's just start with A. It's going to be a separate problem there. So how many liters of CO? We don't know how many liters there are. Hopefully you've gone through and balanced the equation. But we do know it's going to make 14.7 moles of CO2. So 14.7 moles of CO2. Level 1, yours probably says liters. You can either just change it to moles right here, or I'll post a separate older answer key. Okay, so we know that right here, this 14.7, this number comes right here, and then we've got to work backwards. So 14.7 is what's produced. We started with nothing, and we created some number, the coefficient, times the mole ratio. Well, the mole ratio is 2 over 2. So the algebra we're doing for this part right here is 14.7 is equal to question mark times 2 over 2. Isolate, solve for question mark, divide by 2 over 2, which is 1. You get 14.7. That means during the change, I used up 14.7 moles of carbon monoxide. Well, if you used up that much and there's none left over, that means any number minus itself is 0. You must have started with 14.7. So we started with 14.7 moles of carbon monoxide. So that's where that number comes, right over here. But they want to know liters. Okay, so 14.7 moles, cancel moles, go to liters. They told us this was at STP, so 1 mole is 22.4 liters. So how many liters of carbon monoxide do we have? 14.7 times 22.4, so 14.7 times 22.4, you'll get 329.28. 329.28. Now the last part, ask yourself, are the sig figs right? Okay, they only gave 3 sig figs, so 1, 2, 3. The 9 is the third sig fig, look to the right. That means it'll be 329 liters of carbon monoxide. That's for the first problem. That's for A. Now for B, it says, what volume of carbon dioxide will be produced from the reaction of 42.6 liters of oxygen gas? So we can either erase this and do a whole new BCA table, or I'm going to show you a little shortcut we can take with just using some of the factor labeling. So let's try the shortcut for part B. Okay, so they're telling us there's 42.6 liters of oxygen, but we know that we have to go to moles. So we got to cancel liters, go to moles. So for this one, it's going to be 42.6 divided by 22.4. That gives us 1.901. So 1.9017 moles of O2. So if we know that we have 1.9017 moles of O2, and we want to get rid of moles of O2, and then we can't go straight to liters of CO2, but we do have a conversion factor that will get us to moles of CO2. So this right here, this is your mole ratio. So what should those numbers be for our shortcut? Look up here, look at the mole ratio. The ratio of CO2 is going to be 2 moles for however many for 1 oxygen. So right now, if you take a look at this, we've canceled out moles of oxygen and we're being left with moles of CO2. Now, do we want to end with moles of CO2? Nope. We want to actually get to the volume of carbon dioxide. So the volume, that they're asking for liters. So let's just do one more step here. So we're going to take that times, so we have moles on top. So our next factor, sorry, I ran out of room right here. Our next factor is going to be, we want to get rid of moles, and we want to go to volume, which is liters. And 1 mole is 22.4 liters. If you look at that now, we'll have the moles of CO2 canceling, and we're going to be left with the liters. So we're taking 1.9017 times 2 times 22.4. So times 2 times 22.4, and you should get 85.2. So this is going to be 85.2 liters. And how many sig figs? They wanted 3. That's perfect. That's what my calculator gave me back. That's liters of CO2. Okay, so that's the end of our first page. Let's go to the next page. Got a couple more problems over here. So level 2 chem, this is your page 6. Level 1 chem, this is approximately your page 7. We may have made a couple changes, so either swap them out and follow along with the video or check the PDF I'm going to post. So for this one, number 3, how many liters of oxygen, so liters, that's the volume, are necessary for the combustion of 425 grams of C7H16 if the reaction occurs at STP? Now that reaction occurring at STP is just telling you that we can use the 1 mole as 22.4 liters. Okay, so the first thing is I'm not given moles, I'm only given grams. I have to convert to moles. So if I have 425 grams of C7H16 and I want to get to moles, your brain better be shouting at you, periodic table. So let's go to the periodic table. Oops. C7, so here's carbon, H16, so 7 times 12.01 plus 16 times 1.01, that should get you 100.23 grams. So let's plug in our 100.23 grams. And now we've got to take all the tops, divide by the bottom, so it's going to be 425 divided by 100.23. And that gives us 4.24. We'll call that good. So 4.24, and that's how many moles of our hydrocarbon C7H16 we have. Good. Now we can actually plug this into our BCA table. Remember, only moles in the BCA table. So 4.24 moles of the hydrocarbon. And they're asking us to figure out oxygen. So whenever you have a reaction, usually things like oxygen or water, there'll be plenty of them. So we're going to use up exactly all 4.24 moles of the hydrocarbon during the change, and after there'll be none left over. So the question is, how much oxygen is it actually going to use up? Okay, so let's just say we're starting with more than enough, and then we're going to be using up 4.24 times the mole ratio here, which is 11 over 1. So we need to figure out 4.24 times 11 over 1. Okay, so 4.24 times 11 divided by 1, so 46.64. So we've got 46.64. Now, I know I didn't write that in the right spot. Just hang on for a second here. This is how much we used up right here. I'm just telling you what that number is. So if we had a lot and we used up exactly 46.64, how much is left? Well, if you had infinity and you subtracted 46, what do you have left? Infinity. There'll be excess left over. But this right here, this is how many moles of oxygen we used up. So we can plug that in over here, 46.64. And we want to get rid of moles and go to liters. Your conversion factor, that many, 1 mole is 22.4 liters. So we're going to take our answer times 22.4. So times 22.4. We're going to get 1,044.79. So 1,044.79, and that's going to be liters. Check for sig figs. 1, 2, 3. 1, 2, 3. Now this is going to be easier than I thought. Good. So it's going to be 1,040, because that 4 won't round up. Now, how many sig figs are in 1,040 liters? Oh, we're lucky. We've got 1, 2, 3 sig figs. Okay, that 0 is a placeholder. So our final answer here is 1,040 liters of oxygen. Now, you see I left the rest of this blank. We can go in and fill that in if you want. So we started with none of the products, no carbon dioxide. We started with no water. During the reaction, we created 4.24 times the mole ratio, which for this one is going to be, oops, that should be blue, which is going to be 7. And over here, we created 4.24 times the mole ratio, which is 8 to 1. So let's go ahead and fill those out. So 4.24 times 8, 4.24 times 8, that'll give us 33.92. So we created 33.92. That's going to be moles of H2O. Because maybe in part B or C of the question, they might ask now how many grams of water or how many liters of gas did you get. And we got to take 4.24 times 7 as well. So 4.24 times 7, 29.68. So for this one, it's going to be 68? Yep, 68. And that's going to be how many moles of CO2. Good, we're done with that problem. So let me just highlight what we learned. So one of the important steps is we had to convert to be able to plug this into the problem. So here's our conversion. That's where this number came from. Then we had to figure out how much of the oxygen we used up. And then that's where we came over here and we converted and rounded for sig figs. So I've highlighted the parts of the problem that actually answered the question we were given. Okay, we got 2 more problems on this page. Uh-oh, is this one balanced? Let's go through and make sure it's balanced. So we have Sb2O3, that's antimony 3 oxide. Antimony needs a Roman numeral. It's a kind of sneaky one that we don't usually talk about. Plus carbon is going to give us plain antimony by itself plus carbon monoxide. So it's not balanced. We need to get it balanced. So first thing I'm looking at, okay, 2 antimony. let's get 2 antimony. 3 oxygen. I'm lucky there's no O2 over here, so maybe I don't have to go to 6. Let's just try and get 3 oxygen right here. So far, 2 antimony, 2 antimony, 3 oxygen, 3 oxygen. Now let's check the carbon. 3 carbon? Oh, look at that. 3 carbon. Looks like we're balanced now. Okay, so let's look at the problem. So now that we have my recipe right here, this is where we're getting all the mole ratios from. Make a little note to yourself. Here's where we can pull the mole ratios. It's our recipe. How many ingredients do we have? Well, usually when you're in the chem lab, you don't know how many moles you have, but you do measure out how many grams you have. There's 0.46 grams of antimony 3 oxide. Okay, so that's what we have. We need to get an answer in moles to be able to plug it into our BCA table. Remember, I'm only moles in the BCA table. So, grams, your brain shouts, periodic table. So, SB203. Let's go to our periodic table. SB203. So antimony's molar mass is 121.76. Oxygen is 16. So 2 of those, 3 of those. Add them all up. Check my math. 291.52. 291.52. 291.52 grams per mole. Okay. So then let's make sure we do this math right. So 0.46. Now we're dividing. Take all the tops over all the bottoms. Divide by 291. Oops. So 0.46 divide by 291.52. We're going to get 0.00157779. Okay, so what should we write that as? How many sig figs do they want in the problem? They gave us 2 sig figs. Let's just go to 4. Just give some extra. So 001578. 0.001578, and that's going to be how many moles of the antimony 3 oxide we have. So before the reaction, we've got 0.001578, and we're going to use all that up. So we're going to use up all of that during the change. During the chemical reaction, we're using all of it up, and there will be none left over. What else do we know? That we know we're going to be using some up here, and then there's going to be exactly none left over. And we know that before the reaction starts, we don't have any products, and we'll be creating some kind of positive amount of product during the reaction. So before the reaction, before we make brownies, there are no brownies. We're going to make them, and we'll have some positive number left at the end. Okay, so now we're set up. Let's just go through and answer the bare minimum of what they asked us to. Okay, determine the number of atoms of antimony. So where am I focusing in on? I really only care about this column right here. This is going to give me moles of antimony, and then I'm going to take the number right over here into my want side. I'm going to convert moles to atoms using Avogadro's number. Okay, so we're going to be creating 0.001578 times the mole ratio, which is 2/1. How do I know that? Look up to your equation, 2 antimony for every 1 antimony 3 oxide. So 0.001578 times 2. So times 2, 0.003156. 0.003156. Okay, so I'm going to take the number, 0.003156, and I'm going to multiply it by Avogadro's number. This should be interesting. I don't know if I can do exponents on my calculator. Okay, so times 6.022. Ooh. Well, times 10 to the 23rd. Okay, let's just try this. So my coefficient, we'll go old school on this, is going to be 0.019. Okay, now let's think about the powers of 10. I couldn't do times 10 to the 23rd. So if we're taking this number times 10 to the 23rd, this is really times 10 to the 0 times 10 to the 23rd. This would be times 10 to the 23rd. Now we've got to change this number. So 1, 2, this would be 1.9 times 10. Now I moved it 2 places. So this number was smaller than 10 to the 23rd, and I had to move it 2 places. So I've got to change the exponent by 2 places, times 10 to the 21st. This should be our final answer, I think. Let me double check it, and I'll be back with you in 1 second. Good news, I went and grabbed my real calculator, and I did that mental math right. So there's your final answer to 2 sig figs. Okay, we are almost done. This was a long video. Thanks for hanging in there. So our last problem, we have to calculate the mass of water that must be removed or must be used to form 3.5 liters of oxygen gas at STP. Okay, so let's kind of diagram this. Number one, it's not balanced, so we got to make sure we get it balanced first. Okay, so let's just go left to right. Potassium, 1 potassium. That's okay. 2 hydrogen. Uh-oh. Right now, I know that's a problem. So I need to get 2 hydrogen. So let's put a 2 right here. So 2 hydrogen. Now that just gave me 2 potassium. Well, I got to go back over here and get 2 potassium. Okay. So let's just make this a... Ooh, this one's going to be tough to balance, isn't it? So we've got an uneven number already. Let's try and work through this together. So 2 potassium, 2 potassium. 2 hydrogen, 2 hydrogen. Let's call that good for right now. Let's count up our oxygen. We have 2 times 2 is 4, plus 1 is 5 oxygen. Now we need to get 5 here, but don't forget there's 2 over here. So 5 minus 2 is 3. I need to get 3 right here. So 2 times what is 3? 1.5. So this is the right ratio, but we've got to go back and double it. So let's say, okay, we've got 4. Here we've got 2. Here we have 3. And here we have 4. Let's double check that now. 4 potassium, 4 potassium. 4 times 2 is 8, plus 2 is 10 oxygen. Okay, 3 times 2 is 6, plus 4 times 1 is 10 oxygen. Potassium and oxygen are good. Now we've got to worry about that hydrogen. 2 times 2 is 4, and then we got 4 times 1, 4 hydrogen. Whew, we did it. Good. So now we've got the right ratio, 4, 2, 3, 4. They gave us liters of oxygen, but we can't plug liters in. We've got to plug in moles. So 3.5 liters divide by 22.4, and that's going to give us our moles. So 3.5 divide by 22.4, we're going to have 15625. 15625. And that's what number is going right here. 0.15625, and that's how many moles of oxygen gas that were created. So remember, we started with none, and let's do our little algebra trick. Question mark times the mole ratio will give us the number we need right here. So let's do our algebra down here. 0.15625 is going to be equal to question mark times 3 over 2. So how do I isolate and solve? If I multiply by 3 over 2, I've got to divide by 3 and multiply by 2. Okay, so this number, we need to divide by 3 and then multiply by 2. We're going to get 0.1042. 0.1042. And that's going to be my moles of oxygen. My moles of oxygen. This should have been in red. I apologize. That's my question mark. So that means I started with 0.1042 moles of oxygen. That number comes right here, times 3 over 2. Here's a good double check we can do. We can take that number times 3 over 2. So times 3, divide by 2. Oops. Uh-oh, something went wrong. Let's try that again. 0.1042. Oh, now I lost my calculator. Oh, we're struggling today. So here's my calculator. Nope. Okay. Here's my calculator. So we're going to take 0.1042, and then we're going to multiply by 3 over 2 times 3 equals, divided by 2 equals, and we get 0.1563, which is what we had essentially right here. So that means that when I go backwards and redo my work, I should get the same answer, and I did. Good, we got there in the end. So this number, my 0.1042 moles of water, I need to convert the moles to grams. So we go to our handy dandy periodic table of science. Let's find the molar mass for water. So 2 hydrogen, so 2 times 1.01 plus 1 oxygen, 18.02 grams per mole. So water has a molar mass of 18.02 grams per mole. Okay. Oh, come on. It's not cooperating today. So you need to clear this all out. 0.1042 times 18.02. We're going to get 1.8776 grams of water. Last thing, check for sig figs. They only need 2 sig figs. So 1, 2, look to the right. That's going to be 1.9 grams of water. And that's it. We did it. You're done. Great work, ChemStars.